Um, Hello, everyone. Um, we will solve an example question regarding the central limit theorem. But before getting into this, let's make a small probability reminder. Right? So remember, we have the random variables, just like die toss or coin toss, sorry, the number of customers in a bank, right? In fact, we have two types of random variables. Um, so this type, so these random variables refer to counting, okay? So this is the coin toss. Well, it's the number of heads, the number of tails, the number of customers, the number of ones, six, twos. These refer to something special for counting. And the corresponding random variables are discrete random variables. Remember, we have a Poisson random variable, which is generally used for modeling the number of customers in a bank, for example. Or we use binomial random variable to show the number of heads or the number of ones that comes in a die toss or coin toss. The random variables like the height of a person or the income of a worker or the lifetime of a lamb, these refer to measuring, right? Measuring. So this is for counting. And these random variables are modeled by the continuous random variables, like exponential random variables or normal random variables. Well, normal random variables are extremely important, and the whole statistics, the notion of statistics is based on normality. So the random variables generally shown, not generally, but they are shown by the capital letters. Okay, so capital X show the random variables. So when you see the random variable, capital letter, it shows the random variable, and if you have to read it, you have to read the definition of that random variable, right? So the small letters show a value of random variable. For example, 7, x equal to 7 means that, well, this is a particular value of a random variable assumed by this random variable x. So we will have some notations like this. What does this mean? This is written like this and read as the probability that the random variable x is greater than or equal to the scalar 7 or 7 directly, right? Again, the probability that the random variable x is greater than or equal to 7. So how to calculate the probabilities? Well, we are lucky because scientists have developed the probability functions for different types of random variables, right? So for example, if x is normal with mean 10 and standard deviation 2, what is the probability that the random variable x is smaller than or equal to 7? So remember, you have to take the integral. So this is not 0, of course. This is minus infinity. Sorry for this. You take the integral. Remember, the normal random variable, it's something like this. It's a curve. It's a bell-shaped curve. You take the integral from minus infinity to 7. So let's say it's something somewhere. So the center is 10, right? So you take the integral from here to 7, from minus infinity to 7. And this is the integrand that you should take. But of course, we are lucky because what we do is we just standardize them, right? And use tables. Okay. So for any normal random variable, what we do is we just standardize this normal random variable, which means that we transform it to another random variable, a standard normal random variable, and then use tables to find the probabilities, right? So Z as the standard normal random variable, right? So this is a universal notation. Z is the standard normal random variable. It's a normal random variable with mean 0, okay, and with standard deviation 1. So this is it's 0 and the standard deviation is 1, okay, means equal to, and that's equal to 1. That's the standard normal random variable. So in order to find the probability that x is smaller than or equal to 7, what you do is you subtract the mean, right, from both sides and divide both sides by the standard deviation, right? So so this is a random variable minus mu. What is mu? It's a constant. divided by sigma, that's a constant as well. So this is a function of a random variable. But the thing is, and the function of every function of a random variable is a random variable itself. And the thing is that, well, um, so if you subtract the mean and divide by the standard deviation, if you subtract the mean from the normal random variable and divide it by its standard deviation, then what you have is z, the standard normal, right? So here you also subtract mu and divide it by sigma minus 10 divided by 2. So this is z, right? Hence, this inequality, this probability expression is equal to what? Is equal to the probability that z is smaller than or equal to minus 1.5. So in order to find this, you need to find the probability that z is smaller than or equal to minus 1.5, right? Okay. So what you can do is you can just plot this, right? So for example, this is what? This is z. So it's better plotting. I'm just plotting it whenever I'm available. Minus 1.5. I will try to find this probability here. Okay. And in order to find the answer, we just go to the book, okay? Or we just look at the tables at the end of the book. Okay, so um, this is the table from the book, right? So to find the probability or the area under the normal curve. So how to use this table? For example, let's try to see what is, for example, what is this value? Let's say this value 0.0274. So in fact, this is equal to, this is 1 minus 1.9 minus 1.92. So you read the binary digit from here and the first digit after the point here and the second digit after the point from here. Okay, so this is equal to the probability that z is smaller than minus 1.92. This is equal to 0.0274. Or let's read this. Let's read the, or let's take another something here. 0.091. Okay, so this is minus 1.34. So this is minus 1.34. That's equal to 0.0901. Okay, so how to find the probability that we have in the question? So what is the probability that z is smaller than minus 1.5? Minus 1.5 is just here, minus 1.50 in fact. So that's equal to 0.0668. So this is probability that z is smaller than 0.0668. Okay. Sorry. Okay, I get tired. So this is what? Z is smaller than minus 1.5, which is equal to 0.0668. Okay, so the question's answer is 0.0668, which is equal to almost 6.7%. So the probability that Z is smaller than or equal to minus 1.5 is equal to 6.7%. Okay. Um, so Okay, so this is how we read the table. Finally, finally, not a new topic, but a different notation. So Z sub 005. What does this mean? Z sub 005. It shows the value, Z value, okay, which leaves an area of 0.05 to the right. Okay, so for example, so this is a plot where you have the area here as 0.90 and this is a symmetric. Okay, sorry, so uh, this part for z, right? This part is for z. Okay, this is for z, and this area is 0.05. Okay, and this area is 0.05. Okay, and the area, so this 1.645 is equal to what? This is the z value which leaves an area of 0.05 to the right. Okay, so this is z005. How about minus 1.645? That's equal to, since this is symmetric, this is equal to minus z 0.05. Okay, so this is minus z05, or this one, since the area to the left of this is 0.05, the area to the right is what? The area to the right is, let me, um, okay, so the area to the right, which is this part, okay, which is this part, so this area is, this yellow area is equal to 0.95, right? So in fact, this is what? Sub 0.95, okay? So Z sub 0.005 is, which leaves an area of 5% to the right, is 1.645, okay? Or for example, let's try to find Z, see 1645. If you just look at here, one, this is 160, 160, 162, 63, 64. So 645 is somewhere in between here. Okay, so here, and that's equal to what? That's equal to the average of this, which is 0.95. And the other very famous numbers are, the other very famous numbers are z sub 0.01 and z sub 0.10. The z value that leaves an area of 0.01 to the right, and the z value that leaves an area of 10 to the right, 10% to the right, okay? And we can in fact find them from the table. Let's see. Okay, so here I want to find z sub 0.10, which means that it leaves an area of 10% to the right. Okay, so this is z. So this is z sub 0.10, which leaves an area of 0.10 to the right. What does this mean? You can write this. The probability that z, capital Z, the random variable z, it's the probability that z is greater than z sub 0.10 is equal to what? That's equal to 0.10, right? Why? Because the probability that capital Z, the random variable Z, is greater than this part is given by this area, right? Which is equal to, by definition, 0.10. So, well, I need to find, so how about this area? How about this blue area, the remaining area? That's equal to 0.90. So what I will try to find is the 0.90 area there, 0.90. Where is that? 0.90 is almost there, right? Almost there. Look at this one, 0.90. So you can write 1.90, 1.28, sorry. So you can write here probability that z is smaller than z sub 1.28 is equal to what? 0.90, or probability that z is greater than z 1.28, that's equal to 0.10. Okay, therefore z sub sorry for this is not z, but this is what? This is 1.28, 1.28, sorry for this. Probability that z is smaller than 1.28 is equal to 0.90. The probability that z is greater than 1.28, that's equal to 0.10. So in fact, 1.28 is what? 1.28 is 0.z sub 0.10. And finally, let's try to find, um, let me erase this part. Okay. And let me try to find now probability that, let me write it with another pen. Probability that z is greater than z sub 0.01, that's equal to what? 0.01, right? Because if you plot this again, I have a z here, and the area to the right of this is 0.01, so this is z sub 0.01. Or this is equal to probability that z is smaller than z sub 0.01, that's equal to 0.99. So from the table, I will try to find um, from the table, I will try to find 0.99, which is there, okay? This is what? This is 2.33, just look at here. So the probability that z is smaller than 2.33, that's equal to 0.99, which means z sub 0.01 is equal to 2.33. Okay. Okay, now let's turn back to our center limit theorem question. Now assume that the height of, okay, let me take this question to the whiteboard. Let me take it here so that you can use the table there. Okay, sorry for that. Hmm. Okay, that's great. One last. Okay. Okay. So, well, um, so that's a distribution where the heads of people are normally distributed with mean 170 and with sigma that's equal to 10. So what is the probability that a student coming from the door is shorter than 165? That's easy, right? So x is smaller than 165. So just convert this to standard normal x minus mu divided by sigma, 165 minus mu divided by sigma. Mu comes from here, sigma comes from here. This is z by definition. Z is smaller than 165 minus 170 divided sigma, which is 10. So this is probability that z is smaller than or equal to minus 5 minus 0.5. So how to find this minus 0.5? Okay, so this is probability z is smaller than minus 0.5 minus 0.5. Well, I will try to find this probability. Okay, but well, this is a sorry. Um, so this is a symmetric distribution. Okay, so finding the probability that z is smaller than minus 0.5 is equivalent to finding the probability to the right of 0.5. Okay, so this is the equivalent. So then, in order to find this, if I find the area to the left of this part, then I can subtract it from 1 and find this shaded region. Okay, so I can find this pink region. Okay, this pink region, let's say. Okay, if I can find this pink region from the table, I can subtract it from 1 and find this shaded, let's say um, shaded magenta region, not magenta, but let's say green region. So what is the probability that z is smaller than 0.5? It's here, okay? See, it's there. 0.6915. 0.6915. So probability that z is smaller than 0.5, that's equal to 0.6915. So this is, let's say, almost 0.69. Then the probability that z is greater than 0.5, that's equal to 0.31, which means this is also equal to probability that z is smaller than minus 0.5. This is equal to 0.31. So what does this mean? The probability that a guy comes to the class, and we know that the distribution of the students in Özyeğin University is normal with mean 170 and with standard deviation is with standard deviation 10. Okay, and the probability that somebody comes from the door and he is or she is shorter than 165 is 0.31, or let's say 31%. That's the probability. Okay, that's the probability. Now, the same question, well, what is the probability that the average height of a class with 25 students, okay? The average height of a class with 25 students is shorter than 165. That's a bit different, right? So that's a single guy. A single guy, okay, he can be or she can be shorter than 165, but now we are talking about the average of 25 people, okay? The average of 25 people. Well, is it what is the problem that they are shorter than 165? So this is what? This is x bar with what? With n is equal to 25. What is the distribution of x bar? X bar is normal with mean what? 170 with the same mean. How about the standard deviation? Standard deviation is 10 divided by square root of 25, which means this is 5 and this is equal to 2. Okay, so this is the distribution of x bar. Then let's find the probability that x bar is smaller than 165. Now let's write the probability definition. X bar minus mu of x bar divided by sigma of x bar smaller than 165, mu of x bar divided by sigma of x bar. Now this is z by definition. Why? Because this is a normal random variable. You subtract its mean and you divide it by its standard deviation, or you can write it like, let me just show it here. X bar minus what is mu of x bar? That's mu. What is sigma of x bar? That's sigma divided by root n. Okay, and this is z smaller than 165 minus mu of x bar. This is equal to 170, right? This is minus 5 divided by sigma of x bar, which is what? Which is 2. Okay, let me write this. This is 165, 170, right? Divided by 2. So this is probability that z is smaller than minus 2.5, which is by the same argument that we used before, z is greater than minus 2.5, which is also equal to probability 1 minus probability z is smaller than 2.5. Okay, so let's see it. 2.5. Well, the probability is what? 0.9938. 9938, right? 9938. So this is equal to 1 minus 0.9938, which means this is equal to, what is this? 62, right? 0.0062, which is less than 1%, right? So the probability that the average of a class is shorter than 165 centimeters is less than 1%. You see the difference? Well, one of them is the probability that a student, a single student, right? He or she is shorter than 165. Now, this is the probability that the average height of a class with 25 students, right? Their average is shorter than 165. So this is much more smaller than 1%, and this is almost equal to what, 30%, right? So this is what center limit theorem tells us about the distribution of the x bar.